So, proof by induction. So I was trying to come up with, I was looking on the internet for like nice ways to explain proof by induction. So hopefully I've got there. So I was explaining that we have like different proofs. So we did like theorem proofs, like theorem 11 and theorem 12. So they're called like direct proofs. And then we have our proof by contradiction, which we did for root 2 and root 3. I don't think, do we do another one? Not sure. Anyway, then we have proof by induction. So inductive proofs or proof by induction are similar to direct proofs in which every step must be justified, but they utilize a 3-step process. So this is the 3-step process I was trying to explain or I mentioned in class today. So the basic step, no, that's proof, sorry, can't spell. We prove the statement to be true for n equal to 1. Now, very, very rarely it's not n equal to 1, but basically what we're talking about is the basic step. Sorry, I've just thought of something else now. So I think a good question to answer is, when do we use proof by induction? So on your paper, it's going to be really obvious because it will say prove the following by induction. But essentially, it's this idea that, you know, if you're trying to check if something is true, you can only suggest that it's true if you can prove it for all values of n. So it's not good enough to prove that something works for like 1, 2, 3. You have to prove that it works for 10 million and for, 27,298,000,000. Do you know what I mean? You have to be able to prove that it's true for any value of n. So that's when a proof by induction is used, when you're trying to prove it for any value of n. So I was saying the basic step. So the first step in a proof by induction is the basic step, which is to prove it's true for n equal to 1. Now there are some examples that I remember doing where it tells you that, say we're only using natural numbers that are even. So if we're only using natural numbers that are even, then the basic step is based on the smallest value in that series. So the smallest value for even natural numbers is actually 2. So generally speaking, it's n equal to 1, but sometimes it can be a number bigger than that. But it's really, really obvious in the question. So hopefully when I pick examples, there'll be a couple where it isn't 1. But generally speaking, it's 1. So it's the basic step. The hypothesis step, is where you assume it's true for n equals k. And then the inductive step is where if it's true for n equal to k, then prove it's true for n equal to k plus 1. Yeah? So they're your 3 steps. I was trying to find a decent analogy. It's a tricky enough one, but the steps kind of work as in this girl is trying to climb these steps. Okay? So the first step, the basic step, is to prove that it's true for the first value in the series. So if we're talking about all natural numbers, then the first value in the series is n equal to 1. So essentially what we're doing there is we're proving that this girl knows how to take the first step. We're proving that she can do that, so she can make that transition. The next thing we're doing is, if she can take the first step, we're assuming that she can take any step. So if she can go from step 1 to step 2, we're assuming that she can go from step 100 to 101, and we're assuming that she can go from step 115 to 116. Right? And then what we do is we say that if we're assuming that because she can take the first step, and we've proven that, then we're assuming she can take any step. What we do then is we prove that she can take the next step. So if we assume that she can take the 100th step, we prove that she can take the 101st based on the fact that she could take the 100th. If she can take the 276th step, if we assume that she can take that step, then we prove that she can take the 277th step. And essentially, by making that proof, so by proving that we know she can take the first step, and then by proving that she can take the 276th step based on the fact that she was able to take the 275th step, then we can induce, or we can prove by induction, that she must be able to take any step in this sequence. That is the basis of proof by induction. Okay, that's kind of the clearest analogy I could find. Now, obviously I know some people love to understand. It's not necessary. You need to be able to do the question. So there are 3 types of proof by induction that you have to be able to do for Leaving Cert Maths. So the first one is based on series. And that's the only one I'm going to do today. Okay, so here's an example. So as I said, it will be super clear that you're doing an induction. So prove by induction for all, and like I said, n is an element of natural numbers. So that means our basic step is going to be n equal to 1 because the smallest natural number is 1. And this is the sequence. We're trying to prove by induction that 4 plus 8 plus 12 going up in factors of 4, so the 4n, equals this thing, 2n times n plus 1. Okay, so we do the basic step first. And the basic step is to prove it's true for n equal to 1. All right, so n equal to 1 is the first term in the sequence. So on the left-hand side, on the left-hand side, the first term in the sequence is 4. And on the right-hand side, we're letting n equal 1. So that is 2 times 1 times 1 plus 1, basically subbing 1 in for n, which is 2 times 1 plus 1, which is 2 times 2, which is 4. So the left-hand side equals the right-hand side. So we have proven the basic step. So we've proven that the girl is able to take the first step. She knows how to take one step. Yeah? So then we are going to do, what did they call that one? I call it the assumption step, the hypothesis step. So the hypothesis step, this is just getting her to kind of anywhere in the sequence. So we assume the statement is true for n equals k. So what that looks like is the left-hand side is 4 plus 8 plus 12 plus, so n equals k, so that becomes 4k. And then the right-hand side, n equals k, so it becomes 2k times k plus 1. That's the hypothesis step. Then we have the inductive step. Okay, so we're assuming that if she could take the first step, we're going to assume that she can take any single step in the sequence. So like the 275th or the 894th. We're assuming that she can take that step. So that's what the hypothesis step is. And then we're going to do the inductive step, which is to basically prove that if she can take the 96th step, we're going to prove that she can take the 897th step. And then from there, we can get any basically 2-step combo, which means she can take any step. Okay? So, the inductive step is to prove the statement is true for n equal to k plus 1 based on n equal to k being true, which was the assumption we made in the previous step, in the hypothesis step. Yeah? So we have the left hand, I'm going to have to bring this way down, sorry. So we have that the left hand side is 4 plus 8 plus 12 plus 4k, and then I'm going to do k plus 1, which means I'm basically replacing k with k plus 1. That's the next step. Okay, and that equals the right hand side, which is where I'm going to replace these k's with k plus 1s. So it's going to become 2 times k plus 1 times k plus 1 plus 1. Yeah? So this k got replaced with a k plus 1, and this k got replaced with a k plus 1. I'm just going to tidy that up slightly. So it's 2 times k plus 1 times k plus 2. Yeah? And essentially then you want to manipulate or mess around with the left-hand side and get it to equal the right-hand side. Yeah? So I'm just going to highlight that bit, and I'm going to say that based on our assumption from the hypothesis step, that chunk there, okay, hopefully you can see that that chunk there is the same as this chunk here, yeah, which means it equals this. So I'm going to sub that in place. I'm going to go 2k times k plus 1, and then I still have this bit, so plus 4 times k plus 1. Yep. So I have two terms, and I have a common k plus 1, so I'm going to take it out as a common factor. So I'm going to take out k plus 1, and that leaves me with this, which is 2k, and this, which is plus 4. Okay, nearly there. So I have k plus 1, and then from this second bracket, I'm going to take out 2, which leaves me, so take 2 out of that, leaves me with k, and 2 out of that leaves me with 2. So what I have is 2 multiplied by k plus 1 multiplied by k plus 2, which is exactly the same as 2 multiplied by k plus 1 multiplied by k plus 2. So that equals the right hand side. Okay, so that's the proof finished. But you just have, I'm going to see if I got it here just so we have the language right. So in step 4, I am just going to copy this in because this is always the way you finish it. So you say, if it was true for n equal to 1, and if k plus 1 is true based on k being true, then by induction it is true for all values of n. And that is your little finisher, and you always have to put that in. Yeah? So that is a proof by induction. So I'm going to do another one, just, because why not? So this is also a different series. So again, we have a pattern, and that pattern is increasing, and it's been added together, so it's a series. Again, we have n as an element of natural numbers, which means our basic step is going to be the same. So our basic step is to prove true for n equal to 1. So the left-hand side, n equal to 1 is the first term, and the first term on the left-hand side is 7. And the right hand side, we're going to let n equal 1. So it's 7 over 6 times 7 to the 1 minus 1. So it's 7 over 6 times 7 to the 1 is just 7, and 7 minus 1 is 6. The 6's will cancel, or you can multiply and get 42 over 6. Either way, the answer is 7. So the left-hand side equals the right-hand side, so we have proven that it's true for n equal to 1, so we know the girl can take the first step. Then we have the hypothesis step, so this is where we assume it's true for n equal to k. So that means we get 7 plus 7 to the 1. No, sorry. 7 is 7 to the 1. So 7 plus 7 to the 2 plus 7 to the 3 plus, we're going to sub k in for n. So that becomes 7 to the k. And that equals 7 over 6 times 7 to the k minus 1. That's our assumption. And then we do our inductive step. So our inductive step is prove true for n equal to k plus 1 based on the assumption. Yeah? Oh, sorry. So prove it's true for n equal to k plus 1 based on the assumption. So we do our 7 plus 7 squared plus 7 cubed plus 7 to the k, and then we're going to replace k with k plus 1. So that's my left hand side. And on the right hand side, I'm going to replace k with k plus 1. So it becomes 7 to the k plus 1 minus 1. So again, based on the assumption, so this chunk is this chunk. Yeah. So based on the assumption, the left hand side becomes 7 over 6 times 7 to the k minus 1. Yeah. And then plus that. So plus 7 to the k plus 1. And we're basically now going to manipulate this and try and get it to equal this over here. Okay. Okay. I can't see anything like super obvious to get there quickly, so I'm going to expand this bracket. So this is where a proof by induction is different from other proofs, in that when you get to this bit, the bit where you have to make the left hand side equal the right hand side, you just have to do maths. Whereas, you know, with other proofs, it's learned off from start to finish. So the first couple of steps are learned off, and you do get a lot of marks for the first steps, but at the end, you're just going to have to do maths. So I have to do whatever I know how to do, normally algebra, to make that left-hand side equal the right-hand side. Okay, given there's powers in this, we're probably talking about indices as well. Anyway, so multiplying 7 over 6 by 7 to the k. There's not really a lot I can do because one has a power and one doesn't. But 7 over 6 by minus 1 is minus 7 over 6. So that's grand. And that's plus 7 to the k plus 1. Actually, maybe, if I change this, so do you remember when we did indices, this was the same as 7 to the k times 7 to the 1? Yeah, because when you multiply indices with the same base, you add the powers, so they're the same thing. So I might write that like that. So 7 to the 1 is just 7 multiplied by 7 to the k. K. So 7 over 6 times 7 to the k plus 7 times 7 to the k minus 7 over 6. So I literally just changed the order there because the 7 to the k's are like terms and you can add like terms. Sorry, I don't have a calculator. So these two are from the same family. So like adding like 6x and 7x. I'm going to keep the 7 to the k and just add the two numbers. So 7 over 6 plus 7. Ooh, I don't know, am I getting anywhere here? So that is 49 over 6 times 7 to the k minus 7 over 6. Okay. Just because of what I'm looking for, I'm going to take out 7 over 6 as a common factor because up here is what I'm looking for. So if I take 7 over 6 out as a common factor, I'm dividing 49 over 6 by 7 over 6. Oh, okay. Well, that makes sense. So I get 7. And then I have the 7 to the k. Okay, that's better. And then if I take 7 over 6 out of 7 over 6, that's just 1. As in 7 over 6 divided by 7 over 6 is 1. Now, I'm going to undo. See what I did up here? So 7 times 7 to the k is 7 to the k plus 1. So that's what this is. So that's 7 to the k plus 1 minus 1. Oh, sorry, I put a stupid bracket in there for no reason. Okay, is that what I wanted? 7 over 6? Yes, 7 over 6, 7 to the k plus 1 minus 1. So I've done it. So that equals the right-hand side, which means I've completed my proof. I don't know if I still have it, do I? Yeah, so I can put in my little finisher. So I proved it was true for n equal to 1. I proved it was true for n equal to k plus 1 based on n equal to k being true. So therefore, by induction, it is true for all values of n, where n is a natural number. Right, so that's how you do proof by induction for a series. So what I will do is out here, I'll put in some proof by induction for series and give them a go and let me know if you have any questions. Okay, and obviously if this doesn't work, if this isn't like enough of an explanation for you to understand proof by induction, that's grand. We'll do the extra class next week. All right. Okay, have fun.